Hello everyone, so in this video we're going to talk about fundamental theorem of calculus part 2, and that tells us what happens if first we differentiate our function and then we integrate. And it turns out that this is going to be a really important tool for calculating integrals and avoiding limits of Riemann sums using all the antiderivatives we have. So this is going to be a tool that we use throughout whenever we're finding integrals. So let's see how it works. So suppose we have a continuous function f on ab, then if we want to do the integral from a to b of f of x dx, which so far has been a really complicated thing unless we have the graph. Well, FEC2 says that all we have to do if we want to calculate the integral is to find an antiderivative, plug in b and plug in a, and then subtract them. So we have to find any antiderivative capital F, it doesn't matter which one you pick, and then do f of b minus f of a. So as long as you can find antiderivatives, calculating integrals is now going to be really, really easy. So this is a big relief. And by the way, it doesn't matter what antiderivative we pick. So we said so far there are specific and general antiderivatives, and the general antiderivative we had to add on this constant c. Since here we can use any antiderivative, it makes sense just to use c equals 0. So when you're doing this, pick the antiderivative with constant 0. And yeah, so why did I say that this is a rule that tells us what happens if first we differentiate and then integrate? Remember here, we're saying that capital F is any antiderivative of little f. So that means that the derivative of capital F is equal to little f. So instead of writing little f here, I could write capital F prime. And then the rule would be stated as the integral of capital F prime equals capital F of b minus capital F of a. So this is saying if we first differentiate and then we integrate, well, we don't get back capital F of x itself, but we get back capital F of b minus capital F of a. So we get back something that's like the original function capital F. Okay, but we normally state it in this first way because this way really emphasizes how we can use it to evaluate integrals, right? If you want to find an integral, find an antiderivative, plug in a, plug in b, and subtract them. And since we're going to be doing this thing f of b minus f of a so often, whenever we calculate integrals, we have a special notation. We write f of x, then with a little line from a to b. So with an a on the bottom and a b on the top. Or sometimes we might have square brackets around f of x and then have a and b on the bottom right and the bottom and the top right. Okay, so let's see why this is true, and then we'll do some examples actually using this. So let g of x be this sine derivative of our function, this integral from a to x of f of t that we studied a little bit when we talked about FTC part 1. Well, by FTC part 1, remember that we said that the derivative of this is f of x, right? If we first integrate and then differentiate, we get back to where we started. So g prime of x here is f of x by FTC part 1. So this is saying, if we think about it in a different way, this is saying that g is an antiderivative of little f. Because if we differentiate g, we get back little f. So this is one antiderivative. And this rule that we're talking about, find an antiderivative, plug in b, plug in a, and subtract them. This rule works for this particular choice of antiderivative, right? Because what are we saying? If we want to calculate our integral from a to b of f of t dt, we're claiming this is g of b minus g of a because g is an antiderivative. But what do we get if we go back to the definition of g and do g of b minus g of a? G of x is the sine derivative up to x. So g of b is the sine derivative up to b. G of a is just 0. It's the sine derivative from a to a. That's going to be 0. So here we get the sine derivative from a to b minus nothing. We just have the sine derivative from a to b. Okay, that's the same as the left-hand side. So here the left side and the right side are equal just automatically by the definition of g. So the formula that we want works for this particular antiderivative. Okay, but we claimed it was true for any antiderivative, so why should it be true for all the other antiderivatives as well? Well, remember that we said that any two antiderivatives differ by a constant, right? So any antiderivative is equal to any other, provided we add or subtract a constant. And if we change the antiderivative, so here say instead of having g, we have g plus 10 or g plus 20 or g plus any constant. We're going to have g plus a constant at b minus g plus the constant at a. When we subtract them, the constants are going to cancel, right? So if the formula is true for this particular antiderivative, it's going to be true for any other because the constants are going to disappear. Okay, so it works for one antiderivative, it works for every antiderivative. So that's why it's true. So it's just the consequences of FTC part 1. Okay, so let's see how we can use this to calculate some integrals. Later you're going to be doing many of these. It's going to save you a lot of time with doing limits of Riemann sums. So for instance, if we want to find the integral from 1 to 3 of 3x squared plus 2x, well, all we have to do is find an antiderivative, plug in 3, plug in 1, and subtract. So an antiderivative is x cubed plus x squared. So we are going to write the integral we're after. But we have to evaluate x cubed plus x squared between 1 and 3. So we have square brackets around it with a lower limit of 1, upper limit of 3. And this just means we take our antiderivative and then we are going to plug in 3 and plug in 1 and subtract. So here we plugged in 3, we plugged in 1, and we have to subtract them. Remember where the minus signs go, right? We're plugging in 3, and then we're subtracting everything that we get if we plug in 1. So do be careful if you do be careful with the minus signs. Okay, so we get 3 cubed is 27, 3 squared is 9, minus 2, we are going to get 34. Okay, here is another problem, for instance, that here was the kind of typical problem we did before when we first studied areas and integrals. Find the area bounded by y equals x squared, the x-axis, x equals 0 and x equals 1. And we worked through this using limits of Riemann sums and so on. So let's see how we can do this using FTC part 2. Okay, well, all we have to do is find an antiderivative. So an antiderivative of x squared is x cubed divided by 3. So we take our antiderivative x cubed divided by 3. We evaluate between 0 and 1, so we plug in 1, plug in 0, and subtract them. So we get 1 over 3 minus 0. We just get 1 over 3. So the answer is 1 over 3. And of course, this agrees with what we had before, except it's way simpler. So that's good news. Okay, next up, let me caution you that fundamental theorem of calculus part 2 works great when the function is continuous and everything is good, but it doesn't work if the function is not, or it may not work if the function is not continuous. So do be careful and check the function is continuous, especially because later we're going to be studying improper integrals where we're going to see functions that are not continuous. Maybe they have an asymptote somewhere. Okay, so let me just highlight this. An example sometimes tells 1,000 words. Let's think of the function little f of x is 1 over x squared for x not equal to 0. Okay, an antiderivative is minus 1 over x, right? If you differentiate minus 1 over x, you get 1 over x squared. And let's try to check the two halves or the two sides of fundamental theorem of calculus part 2. So if we just evaluate capital F between 3 and minus 1, okay, if we plug in 3, we get minus 1 over 3. And if we plug in minus 1, okay, you have to keep track of a lot of the minus signs. If we subtract f of minus 1, we're going to get minus 1 divided by minus 1. Okay, you can check, it's a little confusing, but you get minus 4/3, which is negative. So this was the right-hand side of FTC part 2. But the left-hand side of FTC part 2 was the integral from minus 1 to 3 of our function little f, which is the integral from minus 1 to 3 of 1 over x squared. And this is the integral of a non-negative function, right? 1 over x squared is always non-negative. X squared is always non-negative. So here, if we're going to hope to integrate something that's non-negative, signed area of bounded by a non-negative function, the area is all going to be above the axis. It doesn't make any sense that it would be negative, right? So these two sides cannot be equal. Here we're integrating something which is non-negative. Here we have something that's negative. So there is no chance that these could be negative. These could be equal. Okay, so in this case, FTC part 2 does not make any sense. It doesn't work. And okay, as you can guess, the problem is that the thing we're integrating, f of x, it's not continuous at 0. So there is no reason FTC part 2 should work because the function is not continuous. And later we'll talk a little bit more about how we should handle this integral from minus 1 to, integrals of functions that have asymptotes, like here 1 over x squared has an asymptote, a vertical asymptote at x equals 0. We'll talk about that later when we do improper integrals. But for now, just check if you're doing FTC part 2, make sure the function is continuous everywhere. Okay, so that about wraps it up for this video. Remember, FTC part 2, it tells us that if we want to integrate a function, then all we have to do is find the antiderivative, plug in a, plug in b, and subtract them. That's going to be a really great tool for calculating integrals, as long as the thing we're integrating is continuous. Okay, thanks everyone. See you next time.